We've just looked at 4 examples of scientific research drawn from the physical, biological, earth, and behavioral sciences. These are just 4 examples chosen, to be honest, because they're things I find very interesting. But just reflecting on these examples, we can already begin to see the astonishing range of research projects that fall under the heading of science. The research methods used in studying adaptation, the age of the universe, climate change, and theory of mind are different in many ways. Beyond the differences in technique, their domains, their spatial scales, their temporal scales are astonishingly different. Theory of mind develops in a few years, while the light from Cepheid stars can take millions of years to reach the telescope. These differences have led some philosophers to argue that when you take a really close look at scientific practice, you don't find much unity at all. Each discipline or subdiscipline has its own way of looking at the world, and so brings its own tools, methods, and theoretical frameworks to the task. There is certainly some truth to the idea that science is not completely unified, and that there is no master method or recipe that's appropriate in all contexts. Nevertheless, there are certain elements common to all of these examples, and exploring these commonalities will be our task in the next weeks. So what are the commonalities? There are at least 4 major ones. First, all 4 of our examples involve sophisticated forms of observation. Adaptation was studied in Galapagos, the universe by observing with telescopes, climate change by considering weather station measurements, and theory of mind by observing children in the laboratory. Second, simple observation wasn't enough. Evolutionary biologists built up samples for further analysis in the lab and then conduct evolution experiments. Astronomers can experiment, but they can use spectroscopy to learn more about the dynamics of their systems. Climate scientists can't perform global experiments, but they can create sophisticated simulations of the planet's climate. And psychologists rely heavily on experiments, but they can't perform just any experiment. They must keep both children and ethics boards in mind. Third, in each case, it was multiple lines of evidence generated using different experimental and observational techniques that convinced the scientific community of the relevant results. Simplistic pictures of science, such as those that are taught in high school, make it seem like scientific research miraculously uncovers the truth by simply verifying one hypothesis with a single experiment. While this does happen occasionally, research more often looks like the cases I've talked about. Research done by multiple people using different approaches that point in the same direction, or they don't sometimes, like in the case of children's beliefs. Philosophers call this robustness or consilience. Fourth and finally, all of our examples involve the accumulation of evidence over time. Each case involves scientific understanding that improves over time, from an initial sense that the answer is at hand, to greater accuracy and precision in measurements, and a much greater appreciation of what is genuinely needed to explain a phenomenon. While scientists never achieve certainty, this is reserved for logic and mathematics, the accumulation of evidence, especially from multiple independent sources, is the key to increasing confidence that a hypothesis is true. Next week, we will delve much deeper into these issues. We are going to look at the 3 main sources of scientific knowledge: observations, experiments, and simulations, and we will talk about how all of them are examples of empirical knowledge.